Okay, so today we're talking about section 2.9, which is all about the formal definition of the limit. Right? And so remember when we first talked about this definition, when we did the sort of semi-formal version, I warned y'all that there was going to be at least one problem where you need to use the definition of the limit to calculate something, right? Using all the laws and algebraic tricks and so forth that we've learned so far is going to be a lot nicer and easier and more straightforward, and it's definitely going to be the way you want to go most of the time. But when it says use the definition, it means use this thing that we're talking about today. So just keep an eye out for that. You should always keep an eye out for the instructions on any given problem, but especially for points in time like this one where you're definitely going to want to make sure you know whether you're allowed to use the limit laws and all that, or whether you want to use this definition, which is as follows: the limit as x goes to c of f of x equals L if for all epsilon greater than 0, there exists a delta greater than 0, so that when 0 is less than absolute value of x minus c is less than delta, f of x minus L is less than epsilon. Right, so that's a lot of tricky language and some Greek letters thrown in, but it really just says the same thing that we said before, that you can make this distance be as small as possible by making this distance small, right? So delta and epsilon are just measures of how small things are, with a big distinction between them, which is that epsilon is, as my grad school teacher would like to say, an enemy gives you epsilon. Someone tells you what they want epsilon to be. It's up to you to find a delta. You get to say that delta is whatever you want, but you don't get to change epsilon. You don't get to decide anything about epsilon. Someone has told you how small they want this to be, right? And they don't necessarily give you a number. They might just say they want it to be less than epsilon. But epsilon, for your purposes, is a fixed point that you don't get to change. Whereas delta, you get to say whatever you want to say about delta. So, we're going to hop into doing some problems about this. If we recall, when we used the semi-formal definition, we said that we wanted to prove that the limit as x goes to 2 of 2x minus 4 was equal to negative 8. And we did that by looking at f of x minus L, which f of x was 2x minus 4, and L was negative 8. So we simplified that to 2x plus 4, and we made this look like 2 times x plus 2, right? So that's all we did before, and we sort of vaguely hand-waved at that point and said, well, if x is close to negative 2, then x plus 2 is very, very small. So since these two things are equal, 2 times something very, very small is still pretty small, so we're good, right? But here we want to specify that we want to talk about delta and epsilon, right? We want to show that this guy is less than epsilon. So x plus 2 is equal to the absolute value of x minus c, which is less than delta, right? That's something we know, we have set, and it's straightforwardly in there, right? So we want this guy to be less than epsilon, and we know that this piece of m is less than delta. So we decide that this is going to be 1/2 epsilon. Right? And if we plug that in, we get that the absolute value of f of x minus L is equal to 2 times the absolute value of x plus 2, which is less than 2 times delta, because x plus 2 is less than delta, which is equal to 2 times 1/2 epsilon, which is equal to epsilon. Right? So we've got what we wanted, which is that f of x minus L is less than epsilon. Right? And that's all that it comes down to. The tricky bit is figuring out what we want delta to be. And it's always going to be whatever it needs to be to plug in to make this true. So let's do another problem. Now we want to prove that the limit as x goes to 4 of 1 over x plus 1 equals 1/5. Right? So note that this is something that we do already know. Right? This is just using substitution. We can plug in, and we get 1 over 5. Right? So this doesn't take any difficulty figuring out using our laws, but we want to show it using the definition. Right? So that means we need to know what f of x is, we need to know what L is, and we need to know what C is. Right? So f of x is the function we're taking the limit of, L is the thing on the other side of the equal sign, and C is what our variable is going to. Right? So we want f of x minus L to be less than epsilon, and we know that x minus C is less than delta. Right? So our goal here is going to be to rewrite this part of what we want so that we can use what we know. Right? So time to settle in for some algebra. Right? This thing right here, it might be nice if we could get this all looking like one fraction. So we're going to start off doing that. Right, so we multiply top and bottom by 5 on the left, and then we multiply top and bottom by x plus 1 on the right. So we get 5 minus x plus 1 all over 5x plus 5. And it turns out that we get 4 minus x over 5x plus 5. Right? So this 4 minus x looks an awful lot like something we know. And in fact, when we pull apart the pieces here, right, then it becomes even clearer. Absolute value signs let us switch around. Okay, sorry about that. There was a brief distraction that I have hopefully edited out at this point. But I lost my train of thought. So anyhow, absolute value signs let us swap around subtractions. That's one of the nice things that absolute values do. So we're just left with dealing with this piece over here. And there are a lot of ways we can deal with it. And one of them is noticing that, so we're going to take a brief side thing here. We want delta to be small, right? And we can say it's as small as we want. We're going to presume that it's at least, or it's at most 1, right? So that means that we know that absolute value of x minus 4 might be less than, is less than delta, and delta might be less than 1, but there's a transitive property there, so we know that the absolute value of x minus 4 is less than 1. And so if the distance from 4 that x is less than 1, then we know that 3 is less than x is less than 5. All right? And if that's the case, then 1 over 5 times x plus 1 is going to be, at biggest, 1/20th. Right? Because fractions are bigger, the smaller their denominator is. So if we replace x with the smallest version of x possible, then we get 20 out of it. Right? So this is one of the things that we can always do in these cases when we want to simplify something, is that we can go ahead and presume that it's at least less than 1. Right? So close that off. We get absolute value, or this should be less than 1/20th. And so now we want to make sure that this is less than epsilon. Right? And so what that means is that when this piece gets multiplied by 1 over 20, we want it to be less than epsilon. So let delta equal 20 epsilon, or less than 20 epsilon rather. And we get that we're less than 20 epsilon times 1 over 20, which is just epsilon. Right? So if we sort of condensed all this back up to our first piece, we've done all this algebra, less than our last piece, we've gotten that f of x is less than epsilon. Right? So in this case, f of x minus L is less than epsilon when delta is less than 1 and delta is less than 20 times epsilon. So anytime both of those statements are true, for whatever delta we choose, because we get to decide what delta is, they have to give us epsilon, and then we can plug that in and choose delta. As long as we choose a delta that is both less than 1, because that got us this simplification, and less than 20 times epsilon, because that got us this simplification, then we know that f of x minus L is going to be less than epsilon, which was our whole point. Right? So our process boils down to figuring out the 3 pieces that go into our formula, simplifying the statement about what we want with an idea of trying to put the thing that we know in there, right? And we're allowed to, as we do that, make substitutions that, or make presumptions that start from the idea that delta is small. Right? We couldn't presume that delta is bigger than 3 because our base idea is that delta is small, and saying delta is bigger than something might very well come into some conflict. So that's our basic idea when we want to use this formal definition of the limit, which we will want to at least once, right? For the most part, we're going to be using our limit rules and working through problems along those lines. But we do want to make sure we have at least some idea of why those limit rules work, right? What is the base underlying idea behind any of these limits? And that is this formal definition. So there is going to be at least one problem where you have to use this formal definition to figure out what the limit is. So this actually wraps up our chapters our sections that are entirely dedicated to the limit. Next up, we're going to start chapter 3, where we talk about the derivative. Now, the derivative is just a limit, so it's not like we're abandoning limits and leaving them behind and never thinking about them again. The derivative is a limit. The formal definition of it that we're probably not going to use all that much once we get our rules, but it is still a limit, and that's why we've spent this entire chapter on it. So that'll be up next time, and I will see y'all then.